Let's start. Happy to be here. My name is Reid. I'm chairing this session. For technical stuff, I want to encourage audience members to ask questions, which at the end of the talk by putting up your hand. Once I call on you at the end, you'll have to unmute yourself and then ask your question. Hope we can get through all of them. Alternatively, if you want to use the Slack chat, you can do that. But that should only be done for the current talk during the current talk. Otherwise, you can do other things later. So let me start. Our speaker for this lunch, dinner, breakfast, midnight snack talk is Eric Murphy, and he's been leading the ngVLA development for many years now. I'm not sure how many actually. And the ngVLA will be a fantastic instrument. In 2 hours, we'll see if it gets a good rating. It'll go ahead very quickly by the decadal survey. It could be a fantastic complement to the ngEHT because it'll achieve observations up to around 100 gigahertz with about the same baseline lengths that ngEHT uses. Well, EHT uses. And it could be great for studying, the jets down to the cores where they start to come out of the black hole regions. So I look forward to Eric's talk. Tell us about the ngVLA.
All right, thanks, Mark. You do the whole screen sharing. Getting the hang of this to usually only take one work, right? Good?
Yep.
All right, yeah, real pro right now. All right, well, pleasure to be here and talk about the ngVLA in light of this ngEHT conference. I really appreciate the invite. And I think Mark is correct that, the more I've been thinking about it and talking to Shep and others, there is opportunity here for a lot of synergy between the two. And I'll get into that a little bit. Not that I've really thought about it all that hard, but hopefully smarter people than I are thinking about it hard. In this, I'll just go over a quick overview about the ngVLA project, where the project sits, maybe how, the reaction to the decadal report and how we plan to move forward. So quickly, the next generation VLA is a replacement of the VLA and the VLBA, a single facility, transformative new facility that will tackle the what we consider new scientific frontier of thermal milging at milli-arcsecond scales. So, really high angular resolution of faint thermal sources, which was something that people had talked about doing for phase 2 of the VLA upgrade, the EVLA phase 2, the New Mexico array. But I think it was quickly realized that to image these faint sources, it takes a lot of steel on the ground. So, with the VLA hitting its 40th birthday recently, it seemed like the right time to start to push for a new facility to do exactly that. Put a lot of steel on the ground. This requires an order of magnitude more sensitivity than currently available with the VLA, and try to image thermal sources. So the concept is pretty simple. It was a sort of a broad concept that was brought to the community to ask what they would do with such facilities, something that's an order of magnitude more sensitive than the VLA and ALMA, and something that can achieve an order of magnitude higher resolution, angular resolution than the VLA and ALMA. The current projected frequency coverage goes from 1.2 to 116 gigahertz, so H1 to J equals 1 to 0 CO. There are 244 18-meter fixed non-reconfigurable antennas, as well as a 19 6-meter short baseline array to fill in the short spacing missed by the 18-meter antennas, as well as we'll use a couple of those 18-meter antennas in total power mode for zero spacing. But the facility is expected to be located centered at the existing VLA site to leverage existing infrastructure, spread across and concentrated across the U.S. Southwest, and spanning across the North American continent to get those continental scale baselines that Mark was talking about. So the ngVLA is really set to link both two premier radio interferometers that are on the horizon scientifically, and that is the SK and ALMA. So on the left here, these are just two diagnostic blocks to really show where the ngVLA fits within the parameter space achievable by these other facilities. So the left plot shows sensitivity against frequency. And the ngVLA, while the SK is really optimized at gigahertz and below, and ALMA is really built at the high Chilean desert site to access terahertz atmospheric windows. The ngVLA is optimized at 1 centimeter. 33 gigahertz is where the entire facility is, the design is being optimized around. And it's to tackle, certain science. So in the figure on the right, you'll say angular resolution plotted against frequency. And that maroon line going across here really just spells it out. So this is the angular resolution necessary to resolve 1 AU, linear distance, at a distance of 140 parsecs, the nearest major star forming site, to study terrestrial planet formation. And you can see over here on the right where we have the optical ground-based facilities, ELT, GMT, TMT. So while the ngVLA is really being designed to study the formation of terrestrial planets, these other ground-based OIR facilities are, looking at achieving these same angular scales, but looking at rocky planets, terrestrial planets that have formed. So together with what they're trying to do and what we're trying to do is really put a consistent picture together on how terrestrial planets forms. So this at the centimeter wavelength, it's really a sweet spot to study terrestrial planets formation, dense gas history in the universe, and baryon cycling in nearby galaxies. So it really complements what these other facilities, both in the radio and optical, are trying to do and will be doing in the next decade. So the ngVLA project has a org chart. This is the org chart. We have a project director, Tony Beasley, 2 project managers, because 2 is better than 1, maybe. Jill Myers and Willem Esterhaus. Willem Esterhaus comes to us from the Meerkat project. I'm the project scientist. Rob Selina is our project engineer. Thomas Kuzel, also from Meerkat, is our system engineer. And we have a cost analyst, Alexa Melvike. This is just basically to show, since the beginning, we set up our project structure with 10 integrated product teams to follow what the NSF is expecting for an MREFC style project. And that is the goal, to be an MREFC project candidate. And hopefully this is what the decadal report does. It springboards our launch or landing into the MREFC queue. We have a very actively engaged science and technical advisory councils. Mark Reid is one of those actively engaged members, and we really appreciate that. We've worked very hard with the community to build both the science case and consequently the technical design of the facility, and they've really been invaluable along the way. We have 5 key science goals that were put together by our Science Advisory Council. I mean, basically, largely the community. We went out to the community asking for use cases for a facility that had, roughly an order of magnitude improvement in sensitivity and angular resolution over current facilities, and received something like 180 unique observations that the community would like to do. Our Science Advisory Council prioritized this and created these 5 key science goals. As you can see here, they really are broad and disparate. They span studying planet formation to probing the initial conditions of planetary systems and life with astrochemistry, studying the formation and evolution of galaxies over cosmic time, using pulsars in the galactic center as a fundamental test of gravity, and understanding the formation and evolution of supermassive and stellar massive black holes in the era of multi-messenger astronomy. So, the thing to take from this is that, unlike a lot of other facilities that have been thought about over the last decade and currently being built, which are survey driven, producing large amounts of data that will be used by the community for archival studies, the community really pushed for a facility that would allow them to grab the keys, go and execute their science, and then hand them back and let someone else do the same thing. So what we've really designed is a highly flexible telescope to carry out this large, broad scientific program. I'm not going to go through all the key science goals, but probably just talk about this sort of the main killer app, I would say, and that is unveiling the formation of solar system analogs. So on the left here, you see this very famous picture of HL Tau taken by ALMA, and a zoom in here. This is a simulation here on the bottom left of what the ngVLA might see at 1 centimeter for a simulated solar system like solar system with Saturn, Uranus, Jupiter, and Neptune mass planets going around a solar-like star. You can see these Lagrange points where the dust is building up in the protoplanetary disk. In the center here, you'll see a plot of planet semi-major axis against planet mass, illustrating the number of known systems that the NGVLA will have access to. And I think what the most interesting thing is that, of these systems, hundreds of systems that exist, there'll be, there are many hundreds, but hundreds of them will actually have orbital periods of less than 10 years. So we can actually turn this study of planet formation to something that was static into something that is now transient. So this is the same simulation by Luca Ricci showing that if we observe, some of these protoplanet forming disks over a cadence of, months, over a cadence of 10 years, we can actually in real time watch the planets orbit this central star and see how they are forming in real time, which I think is absolutely incredible. Another key science goal is understanding the formation and evolution of black holes. So unaffected by dust obscuration, NGVLA sensitivity and angular resolution will be able to resolve AGN and black hole binaries. So in this plot on the right here, from Sarah Burke-Spolar, this is from her science book chapter, I believe, it's projected nuclear separation parsecs, and to the right is redshift, and this orange area is the area of systems where the NGVLA with its continental scale baselines will be able to measure the proper motions of such binaries over 5-year periods. And these are the progenitors, or many are progenitors of gravitational wave events. So the NGVLA will really provide a new view on studying the electromagnetic radiation counterparts of gravitational wave sources. This is not a key science goal, but it's certainly appropriate for this this audience. And I think one of the coolest things we've done with our community studies program. So over the past 4 years, we've run this program where we ask members of the community to either contribute to the design and development effort of the NGVLA scientifically or through some technical study. And we funded folks for this. This is a simulation done by Kazu Yakiyama and Lynn Matthews of, so the study was really to see how Smiley, the imaging algorithm compared to CASA for a real high resolution case of a pulsating AGB star. So this simulation shows that what the NGVLA at 6 gigahertz would do for a AGB star with a 1.3-year pulse period. This sort of movie it's an observation taken every 2 to 3 weeks. The angular resolution here is 1.5 milliarc seconds, so 400ths of the stellar radii at a distance of 150 parsecs. And I mean, again, this is a case where you take a science or something that was, sort of static, and you turn it into, a real-time real-time transient kind of a science case. I find it amazing that with this facility you'll be able to go and watch pulsating AGB stars and watch real in situ dust formation. Even though that wasn't the goal of this study, this study was, of course, looking to see how Smiley compared to CASA, and the finding was that CASA actually did a pretty good job. Smiley certainly did better in the image reconstruction, and Kazu is actually furthering this sort of study by looking at other imaging cases. But yes, this is just, I find this to be another very cool science case for the NGVLA. So today we've had very strong community participation from the university community, in industrial private sector, as well as international contributions, ranging from our science and technical advisory councils, as well as through our community studies. Today these are images of in-person conferences, which are certainly not the regular anymore. I'm looking forward to getting back and starting these up again. But the point of showing the images, even though they're sort of dated, is to emphasize the fact that the community rallying around the NGVLA is early career. I mean, the majority of folks there are early career, and I think we've done a pretty good job of getting young folks excited about this new facility. And I think this translates into what the decadal report is saying and giving us a pretty high priority right now. Over the past couple of years, we obviously couldn't hold these in-person meetings. We did our best in holding virtual science meetings. We've held two summers of short talk series, which I think were pretty successful. We had roughly, I think, 800 people attending the first year of that. Our community studies have been pretty successful, and we've been holding town halls. But hopefully we're getting through all this, and we'll start to get back to in-person meetings next year. International engagement is ongoing. As I said, through our SAC and TAC and community studies program, we've had involvement from folks from Canada, Mexico, Japan, Germany, the Netherlands, Taiwan. We had our first international science meeting right before the pandemic started to take over. This was September of 2019 in Mitaka, again, full of early career science folks. Most recently in the Canadian Long Range Plan, their decadal equivalent, we were ranked as a highest priority future project, they're looking at a 6% investment. And the NGVLA is currently a candidate being considered as part of the Japanese Master Plan right now, which will come out in 2023. The NGVLA technical baseline, as I said, the frequency range goes from 1.2 to 116 gigahertz. This is covered in 6 bands that are in 2 dewars. The L band basically sits in its own dewar, and the other 4 bands sit in another one. The main array, I'll show an image of this in a second, consists of 214 18-meter antennas that are spread across the Southwest. I had mentioned there's the short baseline array, and then the long baseline array is 30 18-meter antennas clustered in groups of 3 that span the continent. So here you'll see the distribution of antennas. In the top left here, you'll see the US Southwest. We have the center, the blue here is the VLA site. You have these mid 1,000-kilometer baseline length arms spanning into neighboring states, Arizona, Texas, and down into Mexico. And I zoom in here, you see that the NGVLA has a 5-arm spiral. The extent of the spiral is basically the current VLA-8 configuration. And then in center there is the core cluster of antennas that spans roughly 4 kilometers in diameter. And then the top right here, you'll see all of the long baseline array stations. So 2 in Hawaii, California, Washington State, 1 in Penticton, 1 in Greenbank, 1 in Puerto Rico, St. Thomas, and a couple other VLBA stations. So existing VLBA stations plus a couple new stations where there's already existing infrastructure. And you can see that they're kind of paired up. And this is for phase calibration strategy. The antenna concept. So we have, as you may or may not be aware, we do have right now funding to construct a prototype antenna, and that has just kicked off. MTech is the antenna design company located in Germany who will be doing this. So right now for the antenna concept, we went with feed low. Maintenance requirements favor receiver feed arm on the low side of the reflector. So, a couple people, you can just stow the antenna, a couple people in a pickup truck can go work on the receiver cabin. You'll have a mount concept, the mount concept that we have a choice of a pedestal concept for the life cycle cost. We went with motor gearboxes and both axes of motion for drives. And in terms of materials, we really run the gamut here. We have cast and post-machine aluminum panels with a steel backup structure, composite subreflector, and mostly carbon fiber feed arm. In the bottom right, you'll see sort of the key specifications: 18-meter aperture, shaped optics, a surface RMS of 160 microns. Optics is offset Gregorian, 4-degree slew and settle time in 10 seconds, and a reference porting RMS of 3 arc seconds. The front end concept, as I mentioned, it's 2 dewars and 6 bands. The 2 lowest bands, we have quad ridge horns, so wide bandwidth 3 1/4 to 1. Not maximizing sensitivity here. As I said, the telescope is really optimized to operate at 30 gigahertz 1 centimeter. For bands 3 to 5, we have corrugated horns, so 1.7 to 1 bandwidth using waveguide LNAs. Our band 6 that Mark already mentioned, our highest band, goes from 70 to 116 gigahertz, again, corrugated horns with waveguide LNAs. For cooling, we're looking at a 2-stage Gifford-McMahon cryogenic system, although there's still an ongoing sort of trade study to see if Stirling coolers, if there's cost savings there. Software and computing considerations. So the operations concept is a science-ready data product telescope, both for initial observations as well as archival projects. You'll be able to with a good justification, apply for time to reprocess data in the archive. And for first observations, you can imagine putting in a proposal where you both set up the observations as well as put in information that would dictate what your high-level data product is coming out of there that would then be archived. In terms of post-processing, it also shows that storing raw velocities will be tractable when the ngVLA goes into operations. This is, of course, unlike the SKA, and this is because we're basically throttling back cases that blow up the system. Average data rates, we're talking about 7.6 gigabytes per second, designed for a 320 gigabyte per second peak. So a 4-hour observation is roughly 110 terabytes and requires about 1,000 cores to process in a few days. Computing is a 2 billion core hour problem, so challenging, but can be met with sort of off-the-shelf kind of cluster. And this is obviously set by time resolution, spectral resolution, and multifaceted imaging. In the cases where we do, some low frequency full beam wideband imaging, which requires AW projection, which is the cost of 1,000 in terms of processing. These are really the fringe cases. A few percent of the cases really require this. So while demanding, it's not something that we would be doing a majority of the time. So synergies here. So I've not a lot of thought has gone into this, but these are things that have come up in talking to folks. So there is definitely potential for science synergies to be looked at. And I think they're starting to be looked at already by the ngEHT team. So one is sort of maybe the potential for joint ngVLA band 6, 89 gigahertz observing campaigns. I don't know if I got that frequency exactly right, but if the ngEHT is equipped with 3mm receivers for calibration purposes, it's something that could be used with the LBA, the ngVLA long baseline array, either simultaneously or in some sort of an HSA-like observing mode. The ngVLA current observing modes will, accommodate HSA-like observing, so to be able to link up with other facilities. But whether or not this could be, commensal or not, could be something that's looked at. And then this is something TK has started to talk about. What is there a potential for a future higher frequency ngVLA band? I mean, clearly, the antenna specs are not to do millimeter observing, 230 gigahertz observing. There's also not space in the indexer for an extra band. But with the current ngVLA design, there is a lot of effective area there. So even though you lose sensitivity by not having such a highly RMS surface, maybe there is still science to be gained, and it could be potentially improved by a future development of wavefront sensor. Again, TK is the one who's been talking about this. So, I mean, no promises here, but it's something I think that's certainly worth exploring. If there's a compelling science case to be made, there's no reason that something like this could not be looked into seriously. And it would, I think, not strongly affect anything with the current design development effort. In terms of highlights right now.
Couple minutes to wrap it up, please.
You got it. Okay, so as I already said, we had money awarded to us from NSF via an MSIP to carry out the prototype. And going forward, we're just looking forward to react to a positive decadal report, which was just released a little over an hour ago. We're working hard to really get into that MREFCQ, continue to build and hone the ngVLA science case, and maybe kick off the VLA to ngVLA transition soon. So this is second to last slide. I'll just go this quickly. So, we really want to be declared MREFC candidate by NSF. We have about 4 years of design and development work to be done that we'd like to ramp up. We're working on a CODER for next year and starting to really secure international partners in the next year ahead of our PDR, which should be in FY23. And we want a critical design review to be construction ready in 2025. In terms of project timeline, it's just exactly what I said. We're right now just getting word of the decadal review. A prototype should be on the plains of San Agustin in 2023. We want to be construction ready in 2025, early science operations sometime in 2029, and in the mid of next decade be fully operational. So to summarize, the ngVLA as it stands right now is an MREFC ready candidate that will be construction ready in 2025. We're in the development of the conceptual design packet, which is for MREFC candidacy. We continue to be engaged with the community. through our meetings, community studies, and advisory councils. International industrial partnerships are ongoing. And we will have an antenna on the plains of San Augustine 23, which is very exciting. And this has all been really made possible by very strong NSF support to date. Something like, I think, in the order of $40 or $50 million. So that's where we are. That's where we're going. And we're hoping you all want to come along for the ride.
Well, thank you, Eric. That was very interesting. I'd like to point out an historical note. Roughly about 30 years ago, Luis Rodriguez was trying to do the protostellar protoplanetary observations with the VLA, and he arranged to get 43 gigahertz receivers put on the old VLA. This is before even the recent upgrade. So it's great to see that now this, with obviously a lot more sensitivity, that this could really get done. So it looks like Jim Moran has his hand up.
Eric, with respect to sighting the outer antennas, the VLBI type antennas, I was wondering why you have chosen to double up on the St. Thomas antenna, because when we had discussions about what antenna would we drop from the VLBA if the funding situation got bad, the first antennas to be dropped would be St. Croix or St. Thomas. So what is the case? Does that make it because of the high water vapor absorption? So does that make the case for doubling up on St. Croix, or does that not make it?
Well, yeah, I mean, Mark could probably speak to this better than I, but certainly that does double up. If weather's bad in St. Thomas, then in Puerto Rico weather might be okay, so you don't lose that baseline, right? And from I'm not a VLBI user, but from what I understand, that is a pretty critical baseline for a lot of the science cases. And yeah, so the redundancy there, I think, helps you out weather-wise, potentially.
All right, but redundancy-wise, it might be better to double up in Green Bank, for example. I just wanted to bring that up. Okay, I'm satisfied.
Oh, and remember, right? Each of the, well, yeah, I guess in station-wise, each of these stations has 3 antennas, right?
Any other hands? I'm not sure I see any. They haven't popped up here. Oh, there goes Shep. Go for it, Shep.
Yeah, I just couldn't resist. Really great talk, Eric. And as you know, we've modeled some of the approaches that we've taken with the ngEHT on the ngVLA, and we're really happy to talk with you and Rob Salina and others in the project as we think about our way forward too. And this idea of synergy between ngEHT and ngVLA is, I think, pretty important for a number of reasons. And there are a number of people like Kazu Akiyama and Lynn Matthews and Sarah Isaoun, Greg Roloffs, and Don Pesci are working actively on trying to understand these synergies. But on the issue of 230 on the ngVLA, which I think is interesting, I know TK has been thinking about that. The weather has got to be a pretty important issue there too. I mean, some of the sites could work at 230, but what fraction do you think really would have good weather at what time? And would there be rationale to preempt the other great science that you talked about for the 230? I'm just curious about if weather statistics have been factored in there.
Yeah, there are a number of ngVLA memos right now, sort of talking about the availability of 3 millimeters at all the sites. And I think there's going to be a new one that Brian Butler is working on this next year. It's true, many of the sites, it might not work, but I think overall, I think the VLA site itself is doable. And that's a huge amount of the collecting area, right? 80% is just within the plains there. So yeah, where you outfit such antennas, I think you'd have to be very strategic. But yeah, we're continually building up the weather information.
I mean, what made me think is that if you did have a cluster that were good at 230, that would be quite useful. If you could phase up a cluster at 1 millimeter, that would be very powerful, because then you'd have ALMA in the southern hemisphere, ngVLA core potentially at 230 in the northern hemisphere, with ngEHT antennas around, and that would be a formidable horizon dissolving array.
TK.
Okay, thanks, Mark, and thanks, Eric. That was a great talk. Now, with respect to Shep's question for 230, I mean, the winter median for the sites that they've looked at, this based on one of their internal memos, is 3 millimeter median weather. I mean, and for throughout the year, it's 5 millimeter median weather. And below 4 millimeter, we operate at 230 gigahertz on Mauna Kea. So majority of the stations, in my view, would allow operation weather-wise, and it's a question of improving the antennas to deliver the required efficiency. And you know, as Eric also said, that with so many antennas, even a small improvement in efficiency will just have a very big impact. And Shep, I didn't understand why you said preempt other signs. Why would 230 would it preempt other signs?
My experience with oversubscribed instruments like ALMA is that sometimes getting time to do science that would stress the system can be challenging.
Okay, I got it.
We've had a lot of success with the EHT because, you know, we've had success clearly, but there are going to be a lot of people who want to use the ngBLA for a lot of different amazing science. So we may not get all the time we need on it.
All right, thank you.
Okay, I think that wraps up this session right on time. Lindy, Avery, can I pass it back to you guys?